On the final, and we're going to move on to chapter 12 on Monday, if not Friday, and that will be the last chapter. It's 12. That's the last one. Polar coordinates, and we only have 2.5 weeks left of instruction. Then we have the finals week, so 3.5 total. But it's going to go quick, so stay with it. Don't let yourself get all piled up at the end. All right, we'll let that happen. Like I used to. I know that feeling. It's horrible. All right, so all the chapter 11 stuff is still open. Do you have any questions from 11:1? Any problems in there we need to look at? Any questions in 11:2? Anything in 11:2 we need to look at? Have you guys been working on it? No? All right. Well, we're going to dig into 11:3 here. So, .3 is about Taylor series. So we've been talking about Taylor polynomials, and Taylor series is.
Oh, it's outside.
Yeah. A Taylor series is the same thing, except it's not a finite number of terms. They go on forever. Does that make sense? They go on forever. It's the same thing. Now, so that's a Taylor. A special case of a Taylor series, these are centered at A. So that's your center. A special case of a Taylor series is one that is centered at 0. And I don't know why, but this guy got his name on it. A Maclaurin series is a Taylor series centered at 0. Okay? And we tend to look at those the most. All right, we tend to look at those the most. So what I'd like to do here is find a Taylor series for cosine x centered at 0, so it's actually also called a Maclaurin series. All right? We'll talk about those guys maybe on Friday. I have, in my office, I have a book that has a little history blurb on them. I didn't have time. I was going to read it and talk about them today, but I didn't have time to. So we'll talk about that on Friday if I can remember. All right. All right, so we got f of x equals cosine x. And because we're finding a Taylor series centered at 0, also called a Maclaurin series, A will equal 0. All right. So I would say, the question is going to be, how far do we need to go? Because we're going to do this deal where we find f of x, where we write the original function, and then we evaluate it at the center, which in this case is 0. Cosine of 0 is 1. And the question is, how far down do we need to go with these derivatives? I would say it's probably good to get 3 or more non-zero derivative evaluations. 3 or more non-zero. The book, in some cases, only does 2, but when you want to have 2, it's sometimes hard to detect the pattern. You'll see what I mean when I talk about detecting a pattern. All right, so what is the derivative of cosine? Negative sine x. And so the derivative evaluated at 0 is? 0. All right, second derivative. What's the derivative of negative sine x? negative cosine x. And our second derivative evaluated at 0 is negative 1. So cosine of 0 is 1, negative cosine of 0 is negative 1. And so we have two non-zero terms. Let's go for 3. So the third derivative of negative cosine x, positive sine x, because the derivative of cosine is negative sine times that negative is positive. Third derivative evaluated at 0. So one more. Let's do the fourth derivative, the derivative of sine. And now you see we're repeating. We got our original one back here. And fourth derivative evaluated at 0 is 1. Once it starts repeating, there's really no point going further, is there? Because you just repeat that cycle again and again and again and again. All right? So our Taylor polynomial then for cosine, let's see, how do I want to write this? Cosine x equals, we'll plug in these numbers in here with a equal to 0, which is equivalent to this. So f of 0, we have 1, and then f, f of 0 is 0. Cancel that. F of 0 is, come on, Mr. Reimer. 1, I was right the first time. So that's your first term. F prime of 0 is 0, so we'll leave that one out, because 0 times whatever else we have there will be 0. And f double prime, good morning, f double prime of 0 is negative 1, so now we're here to be negative 1/2. Okay. F triple prime is 0, so the next term is 0. And the fourth derivative is 1. So we're going to continue this pattern. This is like 2 factorial, 3 factorial, and so on. So we're going to get plus 1, 4 factorial, x to the 4th. Then it will be minus. I kind of don't like to leave it with a minus. We don't need to do this again, but just looking at the pattern, what will the next one be? Yes, 1/6 factorial. X to the 6th. Plus dot, dot, dot. These are more commonly written as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial to the 6 over 6 factorial plus dot, dot, dot. They're more commonly written that way rather than having the fractions in front, the 1/2, the 1/4 factorial, and so on. That's how it's most commonly written. And now, yeah, they started at 0. We need to figure one of these out. Equals the sum as k goes from 0 to infinity of c sub k x to the k. Let's just write that. So we need to figure out a pattern from here to make this, okay? I usually, when I do this, I first look at the signs. They're alternating, plus, minus, plus, minus, plus, minus. How can I set something up with a -1 to make the signs alternate? -1 squared? There you go. So, does -1 to the k power do the trick?
Yes.
Are we sure? Well, when you put in 0 for k, you're gonna get 1. That's good. In the next round, k is gonna be 1, not 2, it's gonna be 1. Put in 1 for k, you're gonna get negative, so that's good. Put in 2 for k, you're gonna get positive. Yeah, it's working, isn't it? Right? Okay, that's working. All right, x to these powers. This is, remember, when you see a 1 in your head, you can think that's like x to the 0, right? 1 is x to the 0. So x, what can I do up there in the exponent to generate 0, 2, 4, 6, and so on?
Okay.
Just k?
2K.
2k, okay. Is that what you said the first time? Okay, 2k. You see, we got to generate even numbers. So now when we put in 0 for k, we get 0. When we put in 1 for k, 2 times 1 is 2. Put in 2 for k, 2 times 2 is 4. And so on. You see how that's working? All right. Over. Now we have to do something for those factorials and the denominators. And remember, when you see a 1 like this to start out with, that's like over 0 factorial. Because what is 0 factorial? 1. So we got 0, 2, 4, 6. What are we going to put down there?
K factorial. K plus 1 factorial.
There we go, 2k. 2k factorial. So when we put in 0, we get 0 factorial. When we put in 1, 2 times 1, 2 factorial. When we put in 2, 2 times 2, 4 factorial. 3, 6 factorial. Get it? See what's happening? This is equal to cosine x. Isn't that cool? Yeah. That, taken to infinity, is equal to cosine x. We've seen it on Desmos before. I won't take time to do it now. The more terms you take, the more that approximation stretches out. And if you take it out infinitely, then it matches it perfectly to negative and positive infinity. All right, I want you to do the same thing, except for sine x. Okay. Do the same thing. F of x equals sine x. And we're going to be centered at 0. So we're finding a Maclaurin series for sine x centered at 0. Give it a try. Make sure you at least get these results here in your notes. Hopefully you're getting the whole thing in your notes, but at a minimum. Well, I'll put it on the board afterwards. copy me because I might make a mistake. Okay, did everybody agree with this part? And we saw that it actually began repeating right here on the fourth derivative. We got signs back. So 1, 2, 3, 4. Those four are just gonna repeat. Right. Okay. So sin x then equals f of 0. We're plugging this information into this. That's all we're doing. F of 0 is 0. Do I need to write it? No. Would it be wrong if I did? No. If it's a really complicated, might I want to, just so I can see what's going on? I might. Yeah, and you could. Okay. Now, f prime of 0 times x. F prime of 0 is 1, so we have 1 times x. I'll just write x. Next. F double prime of 0 over 2 times x squared. F double prime 0. If I put 0 here, that entire term is going to be 0, isn't it? So I'll leave it out. Now, F triple prime of 0. We got negative 1. So that is minus 1 over 2 factorial x squared. X cubed, I'm sorry. Got this messed up. 3 factorial x cubed. That happened right here. The fourth one's going to be 0. If we continue this pattern for the fifth one, we got positive 1. And this is the fifth term, so that's over 5 factorial x to the fifth. Continuing this pattern, it would be 7 factorial x to the 7th plus dot dot dot. Any questions there? So this is more traditionally written as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. Goes forever. Continue the pattern forever. The first term, do we want to start this at 0? I want to see what they do. I think it's in here somewhere. See here, 0 actually gave us a term. That 1 is the 0 term, so we began it at 0. Does that make sense? Here, 0 will not give us a term. It'll be 0. So I'm going to start it at 1, where the terms actually begin. This is the 1 term, not the 0 term. So again, let's first focus on the pluses and minuses. What am I going to do with -1 to what power to generate these positives and negatives? Okay, if I just put k, it starts at 1. If I put in 1 for k, -1 to the 1 is going to be negative, and this is positive. Negative k, be careful. Remember, when you do negative k, that's equal to 1 over -1 to the positive k. So
The second power.
there, oh, you're getting closer. 2k, there we go. No. Somebody said something plus.
I think k plus 1.
Awesome, that's it right there. K plus 1. So now, when we put in 1 for k, 1 plus 1 is 2, -1 squared will be positive. Put in 2 for k, 2 plus 1 is 3, -1 raised to an odd is negative. Put in 3 for k, 3 plus 1 is 4, -1 to an even is positive. See how it's going to work? All right. X. Now we need an expression for the exponent that generates 1, 3, 5, 7. Generates the odd exponents. Remember, this is x to the 1, so 1, 3, 5, 7. We need an expression up there that generates that when we put in 1, 2, 3, 4, and so on. What's that? If you just put k up there, put in 1, you got x to the 1, that's good. But then you put in 2, we got to get x to the third when we put in 2. K plus 1? Don't write it till we actually find it. I'll tell you when it's good. When we put in 1, 1 plus 1 is 2. That's not a 2, that's a 1. K plus 1 is not going to work. How much do they skip by each time? 2. That tells you it's going to be 2k. If they're skipping by 3s, there you go, -1. Now look. Put in 1. 2 times 1 is 2, -1 is 1. Put in 2. 2 times 2 is 4, -1 is 3. And it will continue working. Everybody good with that? Okay, now we need to generate these denominators. And keep in mind, this is like over 1 factorial. You don't have to, we wouldn't normally write that, but just so you know, that's like 1 factorial. So what would we do to generate those? Perfect. The exact same thing. Those are a match with the exponent. So it's going to be 2k minus 1 factorial. that is equal to sin x. That's equal to sin x. Yes, sir.
Could it get easier to create
This is how you gotta do it. All right, now I want you to make one for